Okay, so now we are interested in the following situation. So what we are interested in is a situation like this. Okay. So here we're playing golf. Here's the golf ball sitting on the tee, and when the club comes in contact with the force, what this is showing you. I'm sorry. Did somebody have a question? Okay. All right. So what this graph is showing you is the force that the club exerts on the ball as a function of time. And this club is in contact with the ball typically for about 50 milliseconds. So that's the kind of phenomenon that we're looking at. Okay, so a very short time phenomenon. Okay, so let's look at this profile of the force. See, the force is 0 before the club comes in contact with the ball. And as the club comes in contact with the ball and the ball compresses, the force gets to be fairly large. And at its peak value, it can be, like I said, 2 to 3,000 times the weight of the ball. And then as the once the compression is complete and the ball takes off, the force again goes back to 0. And again, this will last about 50 milliseconds. If you're kicking a soccer ball, the soccer ball is softer, and so that might last 100 milliseconds. Okay. So for a softer collision, it could last longer. Okay. Now, in practice, we are not interested in measuring this force profile. What we are interested in is the area under this curve, and that is called the impulse. Okay. So, so in situations like this, the area under this curve is called the impulse. And you guys know how to calculate an area under a curve. You do an integral. Okay, so this is what will be the impulse. Okay, now let me also draw a diagram here. So here is the ball sitting on the tee. Let's look at all the forces acting on it. Here's the force of gravity, and there's a friction force in that direction, and there's a normal force. The normal force is equal to the weight, and the force that the club exerts on the ball while it's in contact. And like I said, at peak, this force can be about 2,000 times mg, the weight of the ball. So what we normally do is, for the 50 milliseconds that the club is in contact with the ball, we ignore all these other forces. Okay, this force cancels that force anyway, and the friction force is small. So we said this is the only force acting on the ball. Okay, and to a good approximation, that is correct. Okay, so that's the impulse approximation. All right. So here's what's relevant. Okay. So here's the force profile of the club, the force that the club exerts on the ball, and the area under this curve is what we are interested in. I will let you get. So here's Newton's second law of force equal to dP by dt, and here's an equation. And with an equation, if you can do any operation to both sides of the equation. So let's say you integrate that over time. This is that, and that is the area under the curve. Now we are using vectors here. The force is a vector, so the integral will be a vector. But right now we'll keep things simple. The integral will be a vector, and that vector is what's called the impulse, denoted by J or I in some books. Okay, so there's the impulse. And the integral of this, using the fundamental theorem of calculus, is just change in momentum. Okay, so what this equation, so this area equal to J, which is impulse, and that is equal to change in momentum. What this means is this area, so if the golf ball was at rest, initially this momentum will be 0. So this area tells you how fast the ball will take off, okay? So what we are saying is when I play golf, this area is much smaller than when Tiger Woods plays golf. Yeah, so for Tiger Woods, the area will be like that, and the ball will take off like crazy, okay? So I hope you guys understand that. Okay, so that's the impulse, that's what we mean by impulse, and that's, we'll see in a second, that's the impulse momentum theorem, okay? The impulse imparted on an object is equal to the change in momentum of the object. All right, so oftentimes, like I said, it's hard to measure this force. Okay, so I have a question asking if will we have time to do problems. So here, what I'm going to do is just lecture. You have problem solutions on YouTube. I will solve problems and post them on YouTube. Okay. So here we are just going to do lectures so you guys understand the concepts. Okay. And once you understand the concepts, then you will understand the problems better as well. Okay, so coming back to the slide, oftentimes we're not interested in measuring this profile. All we're interested in is we know how long the force lasts, and we just are interested in the average force. That's the average force. How's the average force calculated? The average force is calculated. You draw a rectangle whose area is the same as this area. Okay, and that's how the average force is calculated, and that's what this is showing you. So the average force is the impulse divided by the time over which the force acts. All right, so here's the important idea that we are interested in: conservation of linear momentum. So let's say here two objects interacting, so they might attract each other, so they might be charged particles, and they're colliding or whatever. There will be internal forces. So Newton's second law says the net force is equal to the time rate of change of momentum of the system. Now these are internal forces, and you can see that these two add up and they add up to 0. So internal forces always will add up to 0. And the net force is any internal force plus any external force acting on the system. Now, as long as there's no external force acting on the system, this will be 0. dP by dt is 0. That means P is constant, and that's what's written here. The momentum of the system before the interaction, before the collision, is equal to momentum of the system after the collision. And that's what is conservation of linear momentum. So for an isolated system, there's no external force and momentum is conserved. So for instance, in the room you're sitting in, there are trillions and trillions and trillions of gas molecules, and they're all colliding billions of times a second. And in all those collisions, since there's no external force, momentum is conserved. Okay. So that's very important. This is a very important principle that we'll use often. Okay. And here's a YouTube link. You can go see about some guy breaking a cue rack, a pool rack, and the momentum right before the cue ball hits the rack is equal to the momentum afterwards. Okay. Anyway, go look at it. Here's an important one in particle physics. Okay, so you have these particles that decay. Okay. So here's a particle that probably lasts maybe a microsecond or something. And if this guy was at rest, he breaks up into these two particles. And since the momentum before him breaking up was 0, the momentum after he breaks up must be 0. So here, these are a particle-antiparticle pair. This is a particle-antiparticle pair, and they have to fly off exactly in opposite direction with equal speeds. That's the only way this momentum will be 0. Okay. And so now they can fly off in any direction, but they'll be going in opposite direction with exactly the same speed. So that's how powerful the conservation of linear momentum law is. Okay, now we'll talk about types of collisions. Okay. But before we do that, let me pause and stop this recording, and then we'll record another one.